Welcome to our NPTEL lectures on the power quality improvement technique. We have introduced and discussed the concept of the passive power filter. Now, today we will discuss in detail about the design of the passive filter. So, the now one aspect we require to understand the sharpness of the resonance which you have studied in your fundamental courses of the power electronics, that plays an important role in the filter design. So, this is the one of the important properties of the passive filter, how you design the sharpness, what is its bandwidth, and it is quantified in terms of the quality factors of the inductor, and it is known as the sharpness of the tuning of the passive filter. As you know, Q will be essentially omega L by R, this ratio. The passive filter is considered to be tuned to the corresponding to the frequency, and we want that some kind of notch kind of compensation. So, thus this Q required to be quite high, corresponding to the frequency at which the inductive reactance is equal to the capacitive reactance, and also it should have a characteristics something like this. You are connecting a passive filter here, thereafter I am drawing the single line diagram. Thereafter you may have a diode bridge rectifier for single phase, let us say. Now, this has to be tuned if it is compensating for the third harmonic. So, the response should be like this. So, you can design the filter some way, third harmonic is 150. So, it has a component of the 150. So, something like this. And again you have an option, you know that you have a problem of the third and fifth. So, you can take little bit of flattened option and something like this will be the response. And there this is third and this one is your fifth, let us say. So, both will be compensated by this where flattening can be less. So, here bandwidth can be more of the 100 hertz, considering the 50 hertz system. This is a third harmonic 150 hertz and 250 hertz, and accordingly you can eliminate fifth and third, and the or you can have if you want have a problem only on the third, then you can take this kind of response and you can eliminate. Thus, this is essentially a band pass filter for it, and this is a notch filter because it is passive, it will eliminate the filtering. So, the passive filter is considered to be tuned corresponding to the frequency or may not be tuned, and you can increase the Q, and so that if this you require to suppress the fifth and seventh or third and fifth, you can tune in a different way, and thus you can get some extent the desirable characteristic, and it is a compromise solution at which the inductive reactance is equal to the capacitive reactance. But in that case you may tune to the fourth harmonic. So, peak may be fourth harmonic, but you can tune third and fifth both. So, then some extent you mitigate fifth harmonic as well as the third harmonic. Here your peak should be attenuate, and it is a notch kind of filter, and there will be a sharp cutoff for the third, and you can see that in fifth that attenuation is not that you will accept. Now, the passive shunt filter is tuned for the lower frequency, are sharply tuned to have quality factor typically 10 to 100 and preferably between 30 to 60. Please understand there is a challenge involved. for this, having a very sharp omega L by R, or that equal to omega CR, whatever may be. So, here value of the resistance required to be very less, and thus what you can understand that you have to increase the R equal to rho L by A, and if you are not connecting an external resistance, then ultimately cross sectional area of the wear and the length of the wear counts, because again you cannot play anything with the L. Essentially inductor is linked with the L. L equal to essentially N phi by I. So, N, this parameter is linked to the length, so number of turns. So, for this reason, so N will be some extent is a function of L. So, ultimately to increase the quality factor, you essentially have to play with the cross sectional area. To have a high quality factor, you require to choose we have a table called AWG, or conductor or gauge, generally AWG. So, you require to choose the higher AWG to have generally close to 60 quality factor, and if you want this kind of thing, you require to reduce the cross sectional area. But look, problem is something else. Since it is a passive filter, it does not matter, but having a higher cross sectional area, essentially this employs the more costs to this solution. Damping, I will take out a separate entity, and it is not totally restricted to the shunt active power filter or the passive filter. It is all required when you are connected to the grid connected system. So, damped filters and the design of the high pass filters are tuned for the high frequencies and have low value of the Q factors. Essentially, you have R and C. So, your value of the quality, it is essentially a damping. So, you have a term of e to the power t by tau, where tau equal to R C. So, it essentially it will have a damp. Generally, when you have a LC, it is a second order system. So, you have a flexibility of the under damped, over damped, all those entity can be there. But here once you have only the high pass, it is just a damping, and you require to keep the value of RC close to your switching frequency. Now, of course, cost depends on various parameter. As I told you, the Q is some extent depend on not only the current rating. One of the advantage of the passive filter is that it does not see the total rating, only it says the voltage rating. Of course, you require to choose the capacitor of the higher voltage rating, but since current will be very low, so power rating of those passive devices, passive filters connected in the shunt path is low, and for this reason we prefer to connect them in the shunt path also. The cost of the passive filter is reasonable and sometimes it reaches this of the equipments. Why? You see that problem lies, let us go to the white page again and take a fresh white page. You already have a bank of the capacitor. To compensate your power factor. Now, what you want in between, you wanted to put an inductor here. So, since it has to compensate the reactive power at fundamental frequency, so current that it will offer to pass, it may be quite high, and you know that omega 5 c equal to under root of L c. So, c is already fixed, and now you have to calculate the value of L. Once you calculate the value of L, it has to bear unnecessarily the high current if you are retrofitting. If you are not retrofitting and it is already you are designing for the fifth harmonic, that is a different issue. So, it has to be an unnecessary this amount of the fundamental current, and this value of L, you know, it is N phi by I. Since value of the I can be very high, and thus the value of the inductance can be low, and you require to meet that inductance, and for this reason you have to meet the higher value of the flux and number of turns. Generally this amount is constant, and essentially you have to, if current value is increased, so you have to play with the number of turns, and thus number of turns can be higher. Since number of turns is higher, and thus it leads to the higher costs. And for this reason we now consider retrofitting this reactive capaciting bank can be converted to the passive filter, that is fine, but it initiates a higher cost many times, and it has to be done case to case basis. Clear? Let us go to our discussions, and for this reason your component costs will be 15 to 20% of the equipment cost. The cost of the passive filters, that is what I was saying in our discussions, that may also be partially supplemented by the reactive power supplied by it. So, in fundamental frequency generally it will be reactive, capacitive power will be more, and it will give you more reactive compensation, and we require to optimize it, and overall minimum cost filter is a minimum capital cost filter which adequately reduces the harmonic at least cost with some part of the reactive power. So, it is a optimization technique. You will find many paper on the cost optimization of the hybrid filter nowadays, not the passive filter. So, ultimately the cost of the reactive power will be there, it will, whether you will be having a band pass kind of thing. So, you can eliminate, since most of the cases it is 3-phase 3-wire system. So, you can eliminate this fifth and seventh with a single filter or not, or you will take 2 notches, this is the fifth and seventh. So, that optimization generally has been done, and we can have a solution, best solution for a particular site with the data. Definitely we have to work with the data. The major part of the capital cost, about 60%, is the cost of the power capacitor. As I told you, this has to be connected with the reactive power compensation, and thus it has been connected to the high voltage line most of the cases, or it sees the total voltage. And for this reason voltage rating of this capacitor is quite high, and as I put it them in series, so value of the capacitor goes low, and you want that value of the capacitor that will be switch on to compensate your reactive power problem, and thus you have a quite big cost coming from the value of the capacitor. Therefore, a reasonable cost reduction may be achieved by proper selections of the capacitor. For designing, so now we come into the important conclusions of our discussions. For designing the data and the nature of the nonlinear load for which passive filter to be designed, we require to know, we as a designer, because whether it is a single phase, then there is a presence of the third harmonic, fifth harmonic, seventh harmonic, whether it is 3-phase 3-wire system, you will have the harmonics like fifth and 7 and 11 and 13. Whether it is a 3 phase 4-wire system, there also there will be a third harmonic, 5th, 7th, then 9, 6 will be absent because of it is a even harmonic, so and so on. Okay. And also you may have a 12 pulse converter. Once we have a 12 pulse converter, we will start with the 11 and 13. So, accordingly the design has to be changed. So, for this reason we say that the design of procedure of the passive filter and they estimate the record of the frequency spectrum of the load, like you just collect the sample and do the FFT. Now, most of the oscilloscope can provide you the FFT and you can get the spectrum of the load, current and its displacement power factor. These are the two important entity. From there you can calculate the THD. There is a link between displaced power factor and the THD. After obtaining the frequency response of the power distribution, equivalent impedance at the PCC, that is point of common coupling, where the passive filter is to be connected, that has to be found out. And most of the cases this we have to add another entity. We now run most of the cases we have a multi-bus system and load is connected one of the bus and you may have a multiple nonlinear load, and we generally run the load flow studies, frequency load flow study, and thus you get the saddle point. So, where the maximum harmonic contamination is there in which bus, and you are supposed to put it at that bus considering the spectrum of the harmonic content at that bus. So, now we require to do something, select the numbers, types and the tune frequency of the passive filters. So, you can go for band tuning and the notch tuning. If you want first the third harmonic one filter for the single phase, fifth harmonic for the one filter, or fifth and seventh harmonic for one filter, or individual fifth for one filter and the seventh for the one filter. So, in that way you will decide the number of the filters. But generally what happen, if you have a very sharp notch, then value of Q required to be higher. If the value of the Q required to be higher, then omega L by R, this value will come, and thus you require to reduce the value of the resistance, and since you cannot do anything with the value of the inductance, already capacitor value is fixed. So, you require to take a higher gauge wire, and for this reason we generally try to compensate like that. It is some extent the optimized solution. Approximately assign the reactive power to be generated by the each of the unit of the passive filters. So, you know that those entity and at the fundamental frequency, and you have already know that history, that what is its reactive power handling capability, and since you have put an inductor, that will also add a negative var, but ultimately you have a knowledge how much reactive var will be compensated by it. Estimate the parameter of the each of the passive filters. So, Q, L, C, thereafter the resistance comes from the ECR as well as the ECL. So, so effective series resistance of the capacitor and the effective series resistance of the inductor. So, evaluate and attenuate the factor of each unit of the passive filter as a function of frequency. You can run a program, generally we prefer to write a program depending on the data, and from there we can find it out the tuning. Check the existence of the resonance frequency of each of the unit of the passive filter. So, whether it is been close to the Q point or not. This one it is matching, but its Q point it is not matching, because it may be tuned to the 6th harmonic if you want to compensate 5th and 7th. The resonance frequencies of the passive filters units are close to the harmonic generated by the nonlinear load. Then we require to do some kind of tuning and change the tuned frequency of the filter. Then we require to run an iterative loop, validate the performance of the distribution system with filter scheme connected to the simulations, and estimate the harmonic distortion, that is THD, of voltage and current and the displacement power factor, and see that whether there is an improvement or not. Sometimes it is challenging, you can improve the power factor, source inductance. For example, you have seen source inductance improves the displacement power factor, and thus directly it reduces the value of the THD. But on the other hand, it will degrade the power factor. So, for this reason we may have some conflicting combinations. Once you want to compensate the high reactive power, then value of the capacitor required to be some value, and unfortunately you may not be able to provide that kind of sharpness, and thus you may not be able to get the IEEE 519 standard by your proper designing. Then you have to increase the value of the inductor, something like that, and that require extra costs. So, that is what I am saying, that you have to iterate and come and converge it. To iterate this design procedure of the passive filter, generally we write a MATLAB code and run it the simulations in a MATLAB Simulink and find the optimal value, that value required to be placed. And you have to take realistically the values of the ECS and the series inductance value, and generally it is not been damped, and sometime it required to be damped. I will show you later why we require to damp. So, otherwise it may cause a resonance once there is a step change. Once there is a step change of the load, this is 5th and 7th harmonic will increase also with the fundamental. If there is a resonance, then that will also propagate. So, all those things require to be damped out. System may be stable, but we require to also analyze its dynamic performance. We are fortunate that active power filter can actively damp your oscillation, but in case of passive we require to put a damping resistance, but that again deteriorates your THD. Iterate the design procedure of the passive filter till satisfactory performance is achieved in terms of the THD of the current, voltage and the power. Now, the passive filter is basically consisting of a series combination of the inductor and the capacitor tuned to a particular frequency. In a single phase system, the 3rd and the 5th harmonic filters are designing using a series tuned filter. There is a reason behind that, because high current has to flow, and for this reason we want that it is a series tuned filter. Please refer to my previous lectures of shunt, series, all those combinations, and C filter. And a high pass filter is designed using a second order damped circuit. Why? If you connect R and C, it is always damped. We do not want, otherwise response will be sluggish. We want L and C, and we put a critical resistance, and thus it is critically damped or very close to the critically damped. So, the response is not sluggish, and also you get a damping, because first order never gives you that control. you always get a damping. So, second order system for this is chosen with the small, not only small, we require to choose a small L and C with a R. And now there is a concept nowadays, instead of this resistance, that is passive damping, you can have a current control and active damping. In a 3-phase system, the 5th and 7th harmonic filters are designed using the series tuned filters, and a high pass filter is designed using a second order damped filter. So, initially the size of the capacitor is calculated, and most of the cases it has been placed, and that value is available to you for a site if you visit the site from the reactive power equipment, but we have to take the de-rating effect of it. Generally it is been placed, if it is 10 years ago, that value of the capacitance will not be same, we have to de-rate the value. The power rating of the equipment QC from the load, and historically you find it out how does the compensation. So, your de-rating should be matched. The absolute value of the capacitance of the Cn is Cn equal to Q by m omega Vs square, where you can have a multiple branches of the capacitor, where m is the number of branches in the passive filter, so that you get a higher value of it, and you have to put some value in series, but it will reduce the value of the capacitor. Ultimately, the combination of the capacitor bank will come for all the phases, and Vs is a per phase fundamental voltage across it, and omega is the fundamental frequency of the supply. So, thank you for your attention. I continue to design the passive filter also in the next class. Thank you.